really nice to give this presentation. The MRI Together program is really a fantastic program. I'm really happy to be involved in this. So I'm going to give some ideas that we have about trying to take that technology that Jacqueline referred to from our sort of, if you like, high resource settings and see what we really have to deal with if we want to take those into lower resource settings. So let me just start off by acknowledging the people on the left who did the science, some of the financial support, and in particular, some of the comments that have come from Josh and Derek and Joseba and Teresa, who have spent a lot of time on the ground, if you like, trying to get these resources working properly. So I want to talk about 4 different topics. So firstly is we're going to talk about low field MRI, obviously. So what can we achieve currently if we have all the resources available? And what are those resources? And then what are those barriers that if we want to take the results that we can get and try and transfer them anywhere in the world, what are the things that we really, really have to think about to be able to do that? And there are a lot of barriers there. And how can we sort of start to overcome some of those barriers? So that's a sort of general outline of the talk. I'm not going to talk about what we call midfield, right? There's some nice work from Siemens here. There's a paper from Vikas Gulani just in radiology. This is another way of looking at a sort of accessible MRI, if you like. And I'm not going to talk about hyperfine, which, you know, on the left, if it works, is great. And on the right, if it doesn't work, then it's not so great. And I think a lot of those company approaches, you know, run into the potential of ending up with a lot of equipment that's due to lack of maintenance contracts or software going out of date or hardware going out of date, etc., can end up here. So I'm going to talk about approaches here where hopefully we can avoid this kind of situation. So low field permanent magnet systems, there's one in the top left from Ziyong Yang's group in China. Ed Wu, you can see on the first whole body system, and then some of the Halbach systems that we have in the lower right-hand side. These are the kind of systems I'm going to talk about. And a lot of the components of those systems can be built locally, and almost all of these are open source. So the plans for these are available. So we can make the magnet, the gradients, the RF, the electronics, and we can write the software, let's say in Python or in PulseSeq, as was one of the previous talks today. Or we can also say some things make sense to build and some things we might actually just want to buy. So for example, we could buy the electronics, some of the RF electronics and the gradients, and also the commercial spectrometer. And I wanted to kind of open the discussion about what we should do. Should we be doing everything open source, or should we be taking advantage of some of the commercial opportunities? So here's the sort of state of the art for what we're able to acquire, let's say on a just below 50 millitesla Halbach-based system, compared to the same person being scanned on a 3 Tesla. So what you can see is image quality, given the difference in field strength, is pretty good. It doesn't look like a 3T, and it shouldn't look like a 3T. But if you look at, in particular, the T2 weighted and the inversion recovery T1 weighted, you can see very good white matter, gray matter CSF contrast, resolutions of the order of about 1.5 millimeters. And so if everything works well, we can get really good brain images. And this is another example here with a little bit of AI denoising going in. And this is looking at, again, in a healthy volunteer, but looking at, this is an older subject, white matter hyperintensities, which you can see very easily on the FLAIR and the T2 weighted scans. So again, these type of scans could be certainly used clinically. And Ed Wu in Hong Kong's, his group have shown some really nice whole body images that again are not trying to compete with a 1.5 or a 3 Tesla, but certainly for pathologies that are relatively large, this could be very, very useful. So if we want to get high quality images, what is important? And if we look at the whole MRI system, we start off with how homogeneous and stable is the magnet. We can then think about from the gradient coils, how linear and efficient are they, and how good is our gradient amplifier. We can look at the RF side and the same thing, how sensitive is our RF coil, and do we have a good RF amplifier? And then the whole of receive electronics, and of course, we have to get rid of any external noise coming in, so electromagnetic interference reduction. So all of those are important. All of those have to work well, but by far the most important thing is the magnet homogeneity. And that's actually one of the hardest things to get right. So why is it such a challenge? Well, if we think about a standard, let's say 3 Tesla superconducting magnet, we have these turns, the solenoid. And if we look at imaging the brain, we can see the brain is really a long distance away from those superconducting wires. And so all of those kind of local highs and lows that come because you're close to the wires are not really relevant, because the brain is such a long way away from the magnet. The filling factor is so small that the homogeneity can be really, really high over that small brain region. If we look at a much smaller portable MRI system, where the magnets are much closer to the brain, you can see that those sort of areas, those red areas where the intensity is very high, those blue areas where it's quite low, just because we've got discrete magnets, those are much closer to the brain. And so the homogeneity of the magnet is going to be worse to start off with, and it's going to be really, really sensitive to where those magnets are placed. And what does that mean for an MR point of view? Well, if the homogeneity is really bad, then simply we will not be able to excite the spins over the entire brain, right? So that we have a certain RF amplitude and pulse length, and typically that will have a certain frequency excitation bandwidth. And even if we make the pulse very short, that bandwidth may not be enough to cover that delta B0. That's delta F that comes from the delta B0. And what that means is we're going to end up with black holes in our image, simply because the spins within where that delta B0 is really bad are not going to be excited. And there is no way of getting the signal back. There's no image processing or anything else that can solve that. So our delta B0, our homogeneity, has to be good enough to be able to excite the entire sample. Even if you could do that, you may end up with image distortions like this. So you can see that the signal is much lower on the left-hand side. It's highly distorted. Now, at least it's excited. So here we can potentially make some corrections here, but the corrections are never perfect. And the spatial resolution is also affected here. And so if we're looking for small regions of interest, we look at contrast changes. These are very difficult to pick up. And again, if the homogeneity is so bad that within a pixel, and our pixels tend to be quite large, that there's a 2 pi or a 360-degree phase dispersion, then again, no image processing is going to be able to bring that signal back. So the homogeneity of the magnet is really, really critical. And what we know is there's different ways of being able to build that. So how might we do that? So 3D printing is a very attractive because it's, readily available. It's very slow, and relatively it's inaccurate. So one ring may not be exactly the same as the other. It's very difficult to get very, very tight tolerances. Laser cutting is also relatively cheap, but it's not accurate because as the laser goes through the plastic, it diffracts. And so if we have our choice, we would go for, say, a CNC mill, which is very accurate, which is what we need, but it's very expensive. And it's also not widely available. So this is where we start to see already this compromise between what is available perhaps very readily in high resource countries and not so much in other parts of the world. Because even if we build it with a CNC mill, we might simulate that our homogeneity looks like, say, 400 or 500 ppm. When we build it, though, we end up with a number which is much worse. So typically way more than 10 times worse. And why is that? That's because we can't machine perfectly. Our magnets might be slightly different field strengths for each individual magnet. And we also have things like demagnetization effects when the magnets are very close to each other. And that's very, very difficult to model. So in order to make a good magnet, we then need to shim. And this is where things get very complicated again, because the algorithms that you need to design your shims to get your delta B0 down are really quite complicated. And again, placing small magnets very accurately, either inside or outside your main magnetic field, is not a trivial thing. You really need to have skilled people who know exactly what they're doing for this. And even then, this often takes 2 or 3 iterations. So the magnet is really, really important. The other aspects, they're important, but maybe less so. So again, you can 3D print. On the left-hand side, you can see a very cheap 3D print. And for some of the imaging, that's going to be good enough. But if you really want to do clinical studies where clinicians are going to want diffusion-weighted scans, you have to be able to have something more sophisticated, that one that can take much more current, can put up with more heating. So you might have, let's say in the middle here, this is an intermediate solution. This is a very high quality 3D print, and then hand wound, so the wires are going into those grooves there. And on the right-hand side is maybe the most sophisticated. So this is from the group of Joseba Alonso in Valencia. So this is a copper plate which has been water etched out. So again, we have possibilities from the very cheap, the very easy, up to the very expensive. And again, it just depends exactly what you need for your particular application. RF coils, again, relatively simple 3D print, but you also need quite expensive wire, this so-called LITS wire, in order to get the highest sensitivity. If you use this normal sort of solid wire, the resistance of that wire is quite a bit higher, and so you're going to lose signal intensity. And again, we come finally to this idea of commercial or home-built consoles. There's many home-built consoles which have been described in the literature. Which are certainly cheaper. You certainly learn more about things, but of course there's a lot of labor and a lot of electronic components that go into that. That may be relatively easy under high resources conditions, not necessarily under low resource conditions. And I'll come back to specific recommendations a little later. And again, getting rid of the interference then, if you've got a sophisticated lab, you can build some EMI sensing coils, you can do some deep learning, you can very effectively get rid of all the noise. But again, it's a complicated engineering solution. Again, this particular example from Ed Wu's group. So what's the sort of, how much difference does this make? So here's a little bit of a sort of timeline within our lab. So if you say in 2017, we really didn't know what we were doing. So we built everything completely self-built, all the electronics, everything, didn't have any noise correction, et cetera, and you end up with a completely unusable image. It's something to get started. You go to 2020, and we've got a little bit better idea about how to build the magnet, and so we see an improvement in quality, but it's still nothing close to what is clinical. We get a little bit better again. I put in a couple of commercial gradient amplifiers on the 2022, and you can see the image now starts to look like a brain image, but there's really no contrast there. And so on the right-hand side, we do a lot of work trying to optimize the sequence parameters, and then we end up with brain images that I showed you earlier, where we can start to really see good white matter, gray matter contrast, lesions, etc. So it's still quite a lot of time that's involved in all of that hardware and all of that software development. So if we say, what do we need to have to build this in a high resource setting? We can say you need high precision machining. You need to be able to have electronics and electronic equipment and things readily available and people to be able to change it. You need to have relatively sophisticated computer facilities, either for processing or for designing these things. And perhaps most important, which is something we don't really think about because we're so used to it, is to have researchers, and these may be students, maybe postdocs, maybe staff, on long-term contracts. So we know they're going to be there for a long time. And each of these has skills in, let's say, different aspects of engineering. And so if we have all of this, we have a chance of getting those very high quality images. Now, if we ask the question, what is really difficult to have in lower resource settings, then you end up with exactly the same list. That this is a challenge in many low middle income countries, but this is exactly what is needed currently with our current design in order to get high quality images. So we have to think, I think, a little bit about this idea of local production versus at least outsourcing part of these systems, because ultimately there's two aims. One, of course, is to learn about how to build an MRI system, and that's very, very valuable. But the other is you have to have a system which is working reliably, which is starting to produce clinical data, because we still need to convince a lot of local clinicians that this approach is really useful. And they'll only see that if we get the highest quality images and we get them every single time. And so how might we try and translate from higher to lower resource settings? Well, the first approach that we took was essentially to take everything that we had constructed, put it into a large crate, take it over, in this case, to Jones Obongolok's lab in Mbarara in Uganda, deliver it there, and run through the entire design process with, in this case, 6 students from all over sub-Saharan Africa. And this was very useful. It really got, I think, the entire idea and project up and running. But of course, it's not a sustainable approach if we're going to look at hundreds or thousands of units within low middle income countries. So we take that one step further and say, how about just local production? So we don't ship things, but that there are facilities, Josh Harper in Paraguay, there was Stephen Jeremy and Anesta Meinches in Cape Town, and then Xiaoying Huang in Singapore. And these are workshops that have been organized with lots and lots of enthusiastic people learning a lot, coming in and building systems. These are head-size systems, and there's been other initiatives like this in New York with Leon and others building smaller systems. And here we end up with, again, lots and lots of local knowledge, but in each of these cases, these systems are not yet at a stage where they can be used clinically. All of this is made possible by efforts like this A4IM. So this is Christoph Kolbitsch and Lukas Winter in particular, who've made a fantastic effort here to put everything that you need to make a system online. So you can see in the bottom left, you can look at all of the console and the gradient system, the magnet, et cetera, et cetera. And as much as possible, all of the outlines and the plans are there, and the magnet then on the right-hand side. This approach then has really a lot of advantages, right? So that if we're thinking about long-term sustainability, then any knowledge that is local that stays there, if personnel can be maintained over a large period of time, this is the ideal situation. It means that MR technicians and radiologists and students and everybody can get involved in the process and really understand what is happening with an MRI scanner. And ultimately, what we would hope is that local commercial production and distribution could take place, with all of this knowledge. So this is really the advantages. But there are some disadvantages, and I don't want to trivialize this, but just to put this, in the sense that there's thousands of cookbooks out there, right? So Simple French Cookery by this very, very famous French chef tells you exactly what to do. But that doesn't mean that you can become a French chef. Since I come from England, then, if I'm going to try and make a sort of national dish here, then having relatively little skills, I'm probably going to end up making something like this. It's probably edible, but it's certainly not what you would like in terms of being very, very high quality. So coming back to this list that we had, at the moment, the designs that we are producing mean that we have to have access to this high precision machining, electronic equipment able to be ordered relatively fast, relatively quickly, and a lot of people with these skills. And without this, then what we're going to end up with systems which are really not fit for purpose in terms of expanding the number of low field systems around the world. And part of the problem, again, back to the cooking analogy, is we're asking too much, right? It's as if we say that to make your recipe, you have to have all this very exotic stuff, which is simply not available in many, many places. So I'd asked Josh Harper, who's probably spent more time in the field than almost anybody else, his thoughts on what we would need to go forward. And I just want to summarize some of the ones that I think are really important. So the first thing is that low middle income country engineers are usually not involved in the initial stages of development. And I think this is critical because we tend to develop things ourselves and then say, okay, now let's see if we can transfer them. But by involving people at a much earlier stage, they can essentially say, that's very nice, but it's irrelevant for us because we don't have that. Or if you could do it in a slightly different way, this would be much more relevant. And so I think going forward, this is something that we have to try and do. We have to look at this troubleshooting techniques, right? That we have certain ways of doing things with sophisticated equipment in high income countries, which are simply not available. And that means that if there's no way of troubleshooting as things go on, that things can go wrong very quickly. So we have to again, find a set of common tools there. And despite all of the efforts and of having sufficient documentation, nobody likes writing documentation. And so there are always details that are left out. There are always things that are come from one source and they're not reproducible. And as he says, and I think truly, it's really difficult for us, even in high income countries, to be able to exactly reproduce the systems. And so we have to change it. And fundamentally then, the designs, I wouldn't say even have to be kept simple, they have to be made simple. And that's going to be one of our major challenges going forward because MRI is not a simple technique. If you think about homogeneity, this has to be in the parts per million. This is a very, very, very sensitive technique. And to think about this open source versus commercialization. And I think he makes a very good point here that open source electronics is not necessarily cheaper. So it may be that you can build your console for 5,000 or something like that. You have to pay somebody to develop it. That person may not be on a long-time contract, etc. So you may end up with something, as he says, which almost works, but actually you might have been better off going with one of the cheaper commercial spectrometers. So I think it's a really, really important debate going forward as to what things should we be producing and what things should we be outsourcing. Gradients, coils, magnets, RF coils, absolutely. We need to be producing those ourselves, but some of the electronics, I think, is an open question. I also asked Derek Jones, who's also traveled extensively, and don't worry, I'm not going through this list, but if you want to look back at this, I think it's quite an insightful list about things that we need to be considering as we go forward if we really want to have a widespread dispersion of this technology. So the conclusions for this, let's be positive. So the end shows some real barriers, but low field has an unparalleled potential to make a real difference in healthcare, right? 0.55 Tesla, 3 Tesla, 1.5 Tesla, it's never, ever, ever going to have the same potential that we have with low field MRI. But our current systems are just too complicated and too fiddly at the moment. And I think one of the things that can be quite misleading, without it meaning to be, is that we publish academic papers and we show good images, we show representative images, but those are with systems that have been tuned and fiddled and everything to make sure everything works very, very well. And so you need a lot of technical support to show that. And so it's important that either we spend more of our time, I think, looking at simpler systems, or we give more realistic impressions of what is possible. So a lot of our research, which tends to be towards making things more sophisticated, really should be focused on making things more simple and more reproducible. I think AI has a role here, but I'm tired of looking at algorithms that make a low field scanner look like a high field scanner. This doesn't make much sense. I think it makes much more sense that we take a low field scanner, which is a simple design, and we're able to turn those images maybe into one similar to one that would come from a low field system, which has a very, very high degree of precise design. And we also need to start acquiring data which is locally relevant pathologies. So that might be hydrocephalus, let's say for Uganda. This might be Zika for some of the sites in South America. And I think we also need to take a serious look at local production, open source, commercial outsourcing, local integration to see what really makes sense, because ultimately we need systems that work reliably to be able to collect the data that people so desperately need. Thanks very much.